Okay, this is our second day of lesson 3.3. As a refresher, we have just been graphing these like constraints, aka these linear inequalities, and then we have some type of objective. So we look for the vertices of our feasible region where all the shading overlaps, plug them into our objective, and this allows us to find mins and maxes. What this is really used for, optimization, is when we're doing word problems. Okay? Now, usually the hardest part for students is reading the word problems and setting up the constraints and setting up like the objective, setting up the equations. Then from there, it's everything we've done yesterday. We're going to graph the constraints, graph the linear inequalities, look for the feasible region, find the vertices, plug them into our objective, and determine if we want to maximize or minimize this depending on what our question is asking us. Okay, so I'm going to read through this. The total number of workers' hours per day available for production in a skateboard factory is 85 hours. Okay, there are 40 hours available for finishing, decks, and quality control each day. The table shows the different hours needed in each department for the two different types of skateboards. If the profit on a specialty board is $65 and the profit for a pro board is $50, how many of each type of skateboard should be made to maximize the profit? What is that profit? All right, so we got a lot going on here. And over here in the table, you can see the skateboard manufacturing time. So we have these two types of boards. I don't know much about skateboarding, but pro boards and specialty boards. Pro boards take 1.5 hours for production and 2 hours to do the deck finishing and the quality control. Specialty boards only take 1 hour for production time and only take a half hour for the deck finishing and quality control. Okay, so the first thing we like to do is define our variables. Okay, and you can go back to that step-by-step chart. But what we're trying to find is how many of each type of skateboard. Okay, that's our goal. So those are our variables. So I'm going to say P is my number of pro boards. S is my number of specialty boards. All right, now I actually like to come up with my objective equation first, because similar to how at the end of the problem, it kind of helps us figure out like what the variables are. At the end of the problem, it also kind of helps us figure out what we're trying to optimize. Okay, so we're trying to find the maximum profit. All right, so when we do this whole like work, we're trying to find like the maximum, which we practiced doing yesterday. So if I'm trying to find maximum profit, that's going to be my objective. I want to find the highest profit. So my equation has to do something with the profit. Okay. If you don't know what profit is, it's basically like, you know, your money coming in, your revenue, and then you have to subtract out how much it makes you to like make the boards, okay, the cost, and your profit would be how much you made. So, for example, if I did your nails and I charged you $40, it only cost me $10 for the supplies, I profited $30 off of that, right? What I made versus what it cost me. Okay, so here they tell us how much we make off each board. They say we get a profit on a specialty board of $65. Okay, P is my number of pro boards. So 65 times my number of, that's specialty boards. Specialty boards, S. Specialty board is $65. Profit for a pro board is $50. So I'll get $50 for every pro board. So my total profit, I'd add these. And you can call this whatever you want. You can call it big P for profit. We use a little p there. So if you want to use a different variable, you can. But there's my objective. This is what I'm trying to find the maximum of, the profit. Okay, I'm just going to switch this over so I remember my constraints. And again, I read that from looking what I'm trying to either maximize or minimize. Okay, because that's what these optimization problems do. They allow us to find the max and the min. Then we have all of these constraints or like kind of like restrictions of these workers, okay? We know that the total number of workers' hours per day available for production, now I'm just kind of going back and looking for like numbers here, is 85 hours. So we only have 85 hours of production time between my two boards here. So looking at my table, it takes me 1.5 hours of production time for every pro board. So 1.5 for every number of pro board. All right, and then my production time for specialty boards is just 1 hour times my number of specialty boards. And I only have 85 hours available. All right, how can I like finish up writing that as like an inequality? I only have 85 hours. Yep, set this. Okay, so we're going to add these. We're going to have a total less than or equal to 85. Good. Okay, there's one of our constraints, right? Kind of one of our like restrictions, I kind of like to say. We can't have any more than 85 hours. All right, then my next piece here, again, I'm kind of going back and looking for numbers. Now I see that we only have 40 hours for the finishing deck and quality control each day. So I come over here and like, oh man, well, it takes us 2 hours for every pro board. And it takes us a half hour for every specialty board. So similar to last one, we only have 40 hours. Now, there's no like specific numbers of constraints you're going to have every time. It kind of just depends on the problem. The other two kind of constraints, and this one you're going to get in the habit of doing every single time with word problems, is that my number of pro boards can't be negative, right? I can't have negative numbers of skateboards. So this has to be greater than or equal to 0, and so does the number of specialty boards. And again, these are going to almost include in every single application problem, because if you're talking about the number of, I think one of the ones on your homework is the number of cakes, okay? You can't have negative numbers, so don't forget these are kind of like, I kind of like to call them like the common sense ones of like, hey, we can't have anything below 0, and that's why we only sectioned off quadrant 1 on our graph. So basically, no matter which axis I call P and which one I call S, I can only be on this side because I can't have negative numbers of skateboards. That's all that means. Okay? So here it doesn't matter. Specialty boards, pro boards are not dependent on another. Which one you call your x-axis, which one you call your y-axis. I just did my number of pro boards down here. Okay? And then leave some room because we're going to have to decide what we're going to count out by in a second. Number of specialty boards here. Just going to abbreviate that. So S up there. Number of specialty boards, number of pro boards down here. All right, so I have 4 constraints in this problem. And again, sometimes it could be 3, sometimes it could be 4, sometimes there might be 5 different constraints. Just kind of depends on the context of the problem, and you just got to read through the data. All right, so these are technically already graphed for us, right? Because P equals 0 is just that horizontal line here. Everything has to be greater. S, that vertical line here, everything has to be greater. Those are kind of already graphed for us. So these are going to have to graph. And like before, I like to personally graph these using x and y intercepts. All right, so I'm going to do this one equation. I'm just going to rewrite it because I kind of ran out of room up there. You don't have to, if you have room on your margins or whatever. I would graph this using x and y intercepts. So what that means is I plug 0 in for x and 0 in for y. Okay, now I called pro boards my x, and I called specialty boards my y. So if I want to find my x-intercept, I'd plug 0 in here. 85 divided by 1.5. I got 56.6. Repeating. I'll make sure that's right. That's right? Okay. For some reason that feels weird, but it's okay to have decimals. It's okay. My y-intercept, I'd plug 0 in here. That's not easy. That just comes out to be 85, right? To divide by 1. And this will also help you decide what to count up by. Okay, we've done problems like this. All right, my other equation is 2p plus 0.5s is less than or equal to 40. So I'm going to do the same thing. I'm going to find x and y intercepts. So this might be a little different from what we did yesterday. And I really only use this strategy, guys, when we do problems that are like just sectioned off to quadrant 1. Okay. If I'm doing like real coordinate plane graphing, I probably would graph it like normal using slope, y-intercept, or making a table. But now, since we're sectioned off to quadrant 1, using intercepts is a really slick method. All right, here, if I plug 0 in for y, which is my specialty boards, I have 40 divided by 2, which is 20.
Bless you.
Here, if I plug 0 in for my x, or my number of pro boards, I have 40 divided by 1/2, which is 80. And again, now I kind of have an idea of what I need to count up by. So I have to get all the way up to 85 and 80. So I counted up by each box as 5. So I said 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. And again, just kind of label every so often. Maybe I'll label like 85, 10, 15, 20, 25, 30, 80 would be here. And same thing on my y-axis. Count up by 5. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100. Okay. Now I have my graph clearly labeled, x and y-axis labeled, counting up by. Now I get to do the fun part of graphing and shading. All right, I'll start with the green equation. So this one has an x-intercept of 56.6 repeating. So this is 55, so 56 is going to be just to the right there. And again, we know what that point is. Okay, we know it's 56.6 repeating. So it's okay to just kind of approximate this. And then this has a y-intercept of 85, which is perfectly right there. Use your straight edge. There's that line. Okay, I'm going to remember to do my helper arrows as we go here. I kind of forgot about that last time. So this line says I want everything less than or equal to this line. So would I shade below this line, underneath it, or above this? Below. Yep. So right now I have like a triangle feasible region right now. Because it has to be everything to the right of this axis, above this axis, and below this line. Now our second constraint has an x-intercept of 20, 5, 10, 15, 20, and a y-intercept of 80. All right, now this one is also less than or equal to 40, so I would be below this one. So now this just kind of like sectioned off even more of my feasible region. So now I need to look where their shading overlaps, which is below both lines, yet above this axis and to the left of this axis. That's this triangle region right here. I would not shade anything to the right of the red line because that doesn't fit that constraint. Okay, everybody with me? After we do that, we find the vertices of this shaded region. So this is, again, why the x and y intercept method is so helpful, because we know what this point is. I'll use blue here. We know what this point is. This point's 20, 0. I always like to label them on my graph. This is technically a point of my feasible region because it's above this line and left here, so 0, 0. And then the other one that boards this triangle feasible region is 80, or I'm sorry, 0, 80. 0, 80. The y-intercept. All right, so those are basically like our 3 possible options for the number of skateboards that fits our constraint. We could have none. We could have 20 pro boards and no specialty boards, or no pro boards, and 80 specialty boards, and that would fit all these constraints. That the production time is less than or equal to 85, and the deck finishing and quality control is less than or equal to 40. So now to figure out which one's going to maximize our profit, that's when we plug these ordered pairs into our objective. So we have our profit equation. Our objective is 65 times the number of specialty boards plus 50 times the number of pro boards. And we're going to plug in, just like we did yesterday, those vertices of our shaded region. We just only happen to have 3 in this case. Okay, I'll do this math for you. Obviously, if I don't sell any, my profit's $0. Okay, my other option, 20 specialty boards, no pro boards. That gives me a profit of $1,000. Just plug that in, 65 times 20. If I have no specialty boards and 80 pro boards, that's going to give me $5,200. So which of these is our highest profit? Yeah, this is our max, right? So to answer their question, how many of each type of skateboard should be made to maximize the profit, and what is the profit? Did you get a different number?
Are these backwards?
Yeah, the 80 goes with the 65 and the 20 goes with the 50.
Yeah,
Oh, did I plug them in backwards?
Oh, yeah.
Ooh, maybe.
She still got the right answer.
Yeah,
Those numbers are right, but
I probably just,
you just gotta switch the.
like these, should be switched, is that what you're saying?
Yeah.
Okay. I probably I don't know what I did. I probably knew what the answer should be.
50 times 80 only equals 4,000.
So, okay, because 20 is this is my P,
Yeah.
and this is my S. Okay, good catch. So I wrote this, I think, the other way on my answer key. 20, yes, there we go. Thank you. 0, 80. Good catch. Probably would have helped me to write the 50p first, but I just wrote it in order of the word problem. Good catch with being consistent with your variables. And that's why, too, some students just like to do X and Y, because then they get less confused. Like, X goes here, Y goes here, and that's fine, too. Okay. Whew, good catch. Did I do that right on my key? No, I didn't. You guys got my back. All right, we're almost done. How many of each type of skateboard should be made to maximize the profit? And what is that profit? Well, the maximum profit is at $5,280. And then the number of skateboards, I have it right here. No pro boards. And 80 specialty boards. For a max profit of $5,200. Sorry, I know there wasn't a ton of room to write there, but hopefully I squeezed it in. And that's what these problems are more commonly used for, are like word problems. But this just kind of introduces you to like the math you're doing here. Now we're like applying it. Okay, but it's kind of cool. I will say, I feel like students' hardest part is usually like setting up the constraints and the objective from the word problem. But then after they get there, they're good at finding the intercepts, finding the feasible region, finding the vertices. Objective 2, I feel like they're good at that. I'm going to also say this. You can use Desmos to help you too. Desmos can graph them for you and just making sure like all your vertices are correct. Desmos can graph inequalities. But again, you have to set the inequalities yourself. Okay, folks, that's our notes for today. We're done. Stop the video.
Goodbye.
watching.